Welcome back from your little ad break. I hope you've got those points all about electromagnetism clear in your mind. Take a note, keep some notes as we're going through this. We're wanting to move on now. We've been talking about how the effect of a current is to produce a magnetic field. And in particular, we focused on the straight conductor. Now we're going to talk a little bit about the loop and the coil. The coil is sometimes called a solenoid. So let's focus on that and make sure that we've got those ideas very clear in our minds. Now remember, up until this point, we've been using the right-hand rule to indicate the direction of the magnetic field. The thumb points in the direction of the current. The field is given by the many fingers. So field and fingers goes together over there. Because we've got one current, we've got many fingers. But when we deal with a coil, it's slightly different. And so we have the right-hand solenoid rule. And I want to just go over the difference here. The first thing about a solenoid is that you have many pieces of wire. So on your right hand, you don't have many thumbs, but you have many fingers. So we swap around and we say many fingers. The current is all going in the same direction on a coil, so we'll use our current direction for the fingers. So the fingers will give us the current direction, and the thumb will do something interesting. It will give us the direction of the North Pole. So just as we've said, we use the fingers of your right hand to give you the direction of the current. And remember, the current here is conventional current. Conventional current means it's from the positive to the negative terminal of the battery. The thumb points in the direction of the North Pole. And the North Pole is like the North Pole of a bar magnet. What we need to recognize at a North Pole of the bar magnet is that the little compass needle would be repelled at the North Pole. And so the direction of the field lines would be out at the north and coming in at the south. Field lines, when we draw them, please make sure, not like my fat pen that I've got, they should be drawn quite neatly and they shouldn't overlap. You usually draw them in pencil. They mustn't cross each other. They must be spaced apart from each other. They never intersect or lie on top of each other, space between them, and they must start and finish on the surface of an object at 90 degrees. So at 90 degrees to the magnet, that's where they'd leave. Okay, so the right-hand solenoid rule, we're going to apply it in a couple of situations. So I've drawn a little picture, sketch of a solenoid. And what you can see here is that it's just pieces of wire, copper wire, wrapped around a piece of plastic or piece of cardboard. This is not a conductor. This is usually an insulator. And we've got this as the coil. Now, if we're going to use the right-hand solenoid rule to establish the direction of the North Pole, well, we'll need to be able to recognize the direction of current. So we haven't been given anything, but I'll just add it in over here. Let's pretend for the moment that that's the positive terminal and that's the negative. So what we recognize here is that the current is going to be moving from positive towards the negative. And so when you use your right-hand solenoid rule, it's going to go, the fingers, many pieces of wire, fingers are going to go up, and the North Pole will be over there, which means the South Pole will be over there. If I was now asked to draw the magnetic field, well, that wouldn't be too difficult. What I would need to do is I would need to be able to say, well, my magnetic field is going to run from the North Pole because this is an electromagnet. It is just like the bar magnet, away from the North Pole towards the South Pole, and I put little arrows to show that, and I'm going to do it exactly the same on the other side, away from the North Pole, all the way around and in at the South Pole. Now, that's on the outside of the bar magnet. On the inside of the bar magnet, the field lines run from south to north. So on the inside, they run from south to north, and we complete them like loops like that. Now, please be aware that we don't always have a completed loop. Sometimes in the field line pattern, we could have just lines coming out like that. They're coming out of the North Pole, and they'd be coming in at the South Pole, and we'd be able to show them like that. So that's the field line, and that's using the right-hand rule. But now things might get a little bit tricky, because we can have different views of a solenoid. And so here's another view of the solenoid. Wonder if you can see what's happened here. That's right. I've cut the solenoid in half, and I'm now looking at it from the top, where the dots and crosses are representing the direction of the current. So again, I'm going to use my right-hand rule, and I'm going to say if the current is coming out on that side, right hand, current is coming out on that side, and it's going in on that side like that, then quite clearly this is the North Pole, and that means that's the South Pole. And if I were to draw the magnetic field again around here, recognize it comes from the North Pole around to the South Pole. And so it will go out of the North Pole and in at the South Pole, and I put little arrows to show the direction. Remember, these lines tell me that the current is coming out at that point and it's going in at that point. And that's how I was able to use my right-hand rule to show it. Now, here's a final picture of a solenoid, which I think is quite interesting, because here we've got magnetic fields, and we're actually looking at the end of the solenoid. So we're looking at one of the poles. And what we recognize is that tells us the magnetic field lines are going in. So this is going in. So when the fields are all going in, that means that this must be a south pole. And so you'll see that here there's high magnetic flux. The field lines are close together, where here the magnetic flux is weaker. What we also recognize is the direction of the current is given by the right-hand rule. So we can say going in on that side, coming out on that side. So the direction of the current is up over there. So that must be positive. It's going around, and eventually it will come out on this side. So if you have a look, coming out on that side, going in on that side. And so we've been able to tell the direction of the current as well. So the right-hand rule is very useful, both the right-hand rule and the right-hand solenoid rule. And guys, I think that more or less wraps up everything that you need to know about electromagnetism. Let's just make sure that we've got the summary sorted out. Remember, around every current-carrying conductor, there's a magnetic field. The magnetic field is perpendicular to the direction of the current. We use the right-hand rules to do that, and we use dots and crosses to represent the direction of either the current or the field.